Good afternoon. This is section 3.1, part A of our transformations chapter. And the topic today is reflection, vocabulary, and notation. For the notes today, you're going to want some colored ink so that you can distinguish your different figures and a ruler. So if you don't have those, pause the video, grab your supplies, and start it up again. Okay, identify rigid motion. First thing you need to know is what is a rigid motion. A rigid motion is a transformation that preserves length and angle measure. So it keeps the same length, it keeps the same angle measures. A non-rigid motion changes length, but not angle measure. So you have rigid, you have non-rigid, okay? Pre-image and image. The pre-image is the original shape. For example, triangle ABC, that could be the original shape. That's the pre-image. The image is the new shape after a transformation has been done. And we designate the new shape using what we call prime notation. So the letters of the vertices are the same, but they get primes. So my image would be triangle A prime, B prime, C prime. A prime actually looks more like this if you were to blow it up. It's a very old symbol, but we usually just make it a little 1 when we're writing it. Okay, so example. Which of the following are examples of a rigid transformation? And so you have a pre-image and an image. So remember, rigid means that it preserves length and angle. Non-rigid preserves angles but not lengths. So looking at A, even though this image is flipped around, you can tell it's the exact same size and shape. That would make it a rigid transformation. The second shape has the same angles, so it still kind of looks like the original, but the side lengths are larger. So that makes it a non-rigid transformation because the shape has changed size. Okay, so really quick recap. When you, on part A, it was rigid, and because it had the same angles and the same side lengths. The fact that it was rotated had nothing to do with it being rigid. So the second shape was non-rigid, which means the same angles but different side lengths. So you might say that in a rigid transformation, the two figures are exactly alike. They might be moved, but they're exactly alike. In a non-rigid, it's an expansion or a contraction of the original shape, but it still looks like the original shape. Okay, flip the page. Part 2. Reflections. All right, definition of reflection is a transformation that reflects each point in the pre-image across a line of reflection. Reflections are rigid motions, so length and angle measures are preserved. If point A is on line M, then the point and its image are the same point. So A is the same point as A prime in the new figure. If point B is not on line M, then line M is the perpendicular bisector of the segment B to B prime. All right, so let's figure out on the figure here what that all means. Oh, I have one more bullet. The reflection of triangle FGH across line M. Oh, this is important. This is your notation. It can be written as a capital R. The line of reflection is a subscript, so M. Then in parentheses, you name the shape, in this case, triangle FGH. Then you have an equal sign where you designate the new letters of the triangle. So triangle F prime, G prime, H prime. And so that is your notation for a line of reflection. You're going to want to pay careful attention to that. Okay, using a ruler, we're going to reflect the figure across the line. First, though, I want to talk about point A. The bullet up above says if point A is on line M, so if I have A sitting right here, when I flip it over the line, because it's sitting right on the line, it doesn't go anywhere. So A prime and A are actually the same point if the point is sitting on the line of reflection. Now, these 3 points are obviously not sitting on the line of reflection. FGH is our pre-image, and we're going to reflect it using a ruler across the line and create an image. Okay, that might help if you turn this just a little bit. And so, when you reflect across a line, you need to draw a line perpendicular to the line of reflection. So that's perpendicular. And then you need to measure how far it is. Centimeters are probably a better idea, just because it's a little more exact. So this is like 3 7/10. So then I'm going to measure the same length on the other side. 1, 2, 3 7/10. And that will be the new point, H prime. So if the relationship between the original point and the new one is they are perpendicular to the line of reflection, and from the line of reflection to H should be the same distance as the line of reflection to H prime. It's really just like you flipped it directly over, almost like you fold your piece of paper over, and that's where the new point lands. Okay, let's do G. So again, we're looking for a perpendicular line. There it is. And it's about 1 3/10. So we're going to go 1 3/10. And that will be our G prime. Again, G to the line of reflection and the line of reflection to G prime are equal lengths. Last one, we're going to do F. So I'm going to draw a perpendicular from F to the line of reflection. It's almost 4 centimeters exactly. So I'm going to measure out 4 centimeters. And this is my F prime. Again, the length from F to the line of reflection is equidistant from the line of reflection to F prime. So now if you do this right, when you connect the 3 vertices, you should get the same size and shape of the original figure. There we are, and this is the image because it came second. Okay, so that's how you do a reflection in space with a shape and a ruler. But there are other ways of doing reflections. One of them is in a coordinate plane. And when we do reflections in a coordinate plane, there's 2 ways to do them. You can do them point to point, or you can do them by counting spaces, assuming that the points are not fractional. So there's a few formulas that will work really well for x-axis and y-axis. So to reflect a shape across the x-axis, you do a capital R for reflection. X-axis goes as a subscript, and then you put every point xy in my shape, and then the right side of the equal sign tells you what math you need to do to that point to reflect it to its new position. The x-coordinate doesn't change at all, but the y-coordinate needs to be multiplied by a -1, and then it will land in a reflection across the x-axis. For y-axis reflection, so capital R for reflection, the line of reflection is the y-axis, so that goes in the subscript. We're going to take every point xy in the figure, and for this reflection, you're going to multiply the x-coordinate by a -1, and the y-coordinate stays the same. So you can actually reflect across the x and the y without drawing a graph or a picture. We call this a point-to-point calculation. Let's practice that. Flip the page. We're going to reflect point 3, negative 6 across the y-axis. Okay, so let's write our formula. Reflection across the y-axis of every point xy equals a negative 1 times the x-coordinate, leave the y-coordinate the same. All right, let's do that. So we're going to start with point 3, negative 6. We're going to use an arrow because it's not really equal. We're going to take a negative 1 times 3, which is the x-coordinate, and the negative 6 will stay the same. So my resulting point is negative 3, negative 6. That is the point reflected across the y-axis. All right, let's practice one across the x-axis. Okay, first the formula. The reflection across the x-axis of every point xy equals, leave the x-coordinate alone, multiply the y-coordinate by a negative 1. All right, so let's do this. We start with negative 2, negative 8. And in this one, we're going to leave the x alone, so negative 2 stays the same, but we're going to multiply negative 8 by a negative 1. The resulting point is negative 2, positive 8. And that's really how you can show your work on your homework. That shows what you did and why you did it. Okay, exercise number 3. We're going to reflect the shape across the x-axis and across the y-axis. We're going to do this using the graph. It doesn't look like the squares on the graph paper printed out very well, so we'll have to do a little bit of dot counting. Sorry about that. All right, let's start with across the x-axis. This is your x-axis. Now remember on the other shape that we drew that the line of reflection is the perpendicular bisector of the line joining each vertex. So if D is a distance of 1 to the x-axis, D prime will be a distance of 1 to the other side of the x-axis. That's our D prime. Now A is a distance of 2, and remember these are perpendicular distances. A is a distance of 2, so we're going to go 2 on the other side. That's A prime. B is also a distance of 2 from the x-axis, so we count a distance of 2 on the other side. It's B prime. And C is a distance of 1, so we count 1 on the other side. That would be C prime. Let me erase that. Okay, so now when we join the points that we've done, we should have a shape. It's the same size and the same shape. It is just flipped over the x-axis or reflected across the x-axis. There we go. There's our new shape. Looks the same. We must have done it right. Okay, we are going to now reflect this shape across the y-axis. We're going to take the new shape and reflect across the y. This is your y-axis. So we're going to start with D. And D is a distance of 3. 1, 2, 3. So D double prime will be a distance of 3 to the other side. So this is D double prime. We use a regular D, and then the new figure is D prime, and then the new figure is D double prime. It shows that they go in order. All right, now we're going to do the rest of these. A is a distance of 4, so I'm going to start to just count spaces. 1, 2, 3, 4. That's my A double prime. B prime is a distance of 6. So I'm going to go straight to the other side, distance of 6. That is B double prime. And C is a distance of 7. So I'm going to go to the left a distance of 7. And that is C double prime. All right, now connect your vertices. You should get the same size and shape of figure, just reflected across the y-axis. Okay, so there is one last reflection I want to go over with you, and we're going to reflect across the line y equals x. This is very common. It comes up on a lot of tests. So when you reflect across the line y equals x, the point-to-point formula is every point switches. So the y-coordinate becomes the x-coordinate, and the x-coordinate becomes the y-coordinate. Now, the line y equals x is a really easy one to follow because it goes through the corners of the graph paper, which let me, because the graph paper didn't exactly work out. There we go, 6, 6. I just went 6 over and 6 across, and I'm going to use that to line my ruler up. So the y equals x line goes through the corners of the graph paper, so it's very easy to plot that line, y equals x. And what we're going to do is we're going to take, and this is a trapezoidal figure, so we're going to reflect across the line y equals x, and it's going to be reflecting trapezoid A, B, C, D, and the resulting figure will be trapezoid A prime, B prime, C prime, D prime. Okay, so remember that this is where the formula really helps. The coordinates are going to actually switch. So right now D is at 3, 1. The new D will be at 1, 3. And you can confirm that that's the right placement because if you draw a line from the original point to the new point, it is perpendicular and the distances are the same. So that's D prime. A prime is 4, 2, so the new A is 4, 2, excuse me. A prime will be 2, 4. Okay, B is 6, 2. The new B will be 2 up 6. And C is 7, 1. The new C will be 1, 7. There is your new figure. Now again, if you can't remember the formula, you can count, and it's hard to see this, but you can count corners of squares. A to the line here is going diagonally through one box. From the line to A prime is going diagonally through one box. So you can actually count the number of diagonals going through the boxes, and it will work out when you're reflecting across the line y equals x. All right, so this was the visual way of reflecting. This was using point to point. Both are ways you need to do things. Be really careful with the notation on your homework. You want to make sure you learn it correctly. Have a good afternoon.